For a century, black holes were the strangest thing the equations of physics produced. The most extreme object the universe permitted. The final answer to what happens when matter collapses under its own weight. We assumed nothing could be stranger. The equations disagreed. When the most massive stars exhaust their fuel, they do not die quietly. In less than a second, a core that outweighs the sun buckles under forces no material can resist. The outer shell of the star falls inward, strikes the collapsing core, and rebounds outward in a shockwave so violent it briefly outshines entire galaxies. A supernova, the most luminous event the universe permits. What survives depends on mass. If the core holds together, compressed beyond imagination, but still recognizably matter, it becomes a neutron star, dense enough that a single teaspoon of its material would weigh 1 billion tons. Extreme, yes. Strange, yes. But still within the laws of physics. If the star was heavier, the core keeps collapsing, past neutrons, past anything we have a name for, until there is no size left at all. A singularity, a point of infinite density with no dimensions, no surface, no structure. A place where our equations stop returning answers and start returning contradictions. Where time and space reverse. A black hole. Black holes have haunted physics since they were first proposed. They are elegant on paper and open wounds in theory. The singularity at the center breaks general relativity. The event horizon appears to destroy information, which quantum mechanics says is forbidden. For a century, physicists have lived with this contradiction, and no one has resolved it. But two theorists asked a different question. What if the core never reaches the singularity? What if at the very edge of collapse, at the last moment before the equations break, something stops it from the inside? At that threshold, the pressure becomes so extreme that matter can no longer remain matter. It transforms. The core becomes pure vacuum energy, the most fundamental kind of energy physics recognizes, and it does not collapse. It pushes back. Violently, an expanding sphere of compressed nothingness, fighting outward against the full weight of a dying star pressing inward. Two forces, both beyond anything in ordinary physics, meet at a single boundary. At that surface, something forms, not a gas, not a crystal, not any material that exists anywhere else in the universe. Something forged at the absolute physical limit of what nature allows. Something with no name, something that holds, a gravastar. From a safe distance, you would not be able to tell the difference. A gravastar curves space-time exactly as a black hole does. It traps light. It bends the paths of nearby objects. It produces every gravitational phenomenon we associate with black holes: time dilation, lensing, the slow spiral of doomed material in an accretion disk. If you aimed a telescope at one, you would see nothing unusual, just an absence, a dark shape against the darkness of space. But the shell is real matter, incomprehensibly thin, thinner than a single particle across, yet so tightly bound that stretching it by a single meter would require the energy of an entire supernova. And it is cold, a billionth of a degree above absolute zero. So cold that the faint background radiation left over from the Big Bang The coldest light the universe contains glows warm beside it. The shell radiates almost nothing. It absorbs almost nothing. It simply endures. The interior is something stranger still. A perfect vacuum. No particles, no radiation, no atoms of any kind. But not an inert emptiness, a compressed one. The vacuum energy inside a gravastar is condensed to nearly 1 billion trillion times the density of the vacuum outside it. It presses outward against the shell. The shell presses inward. Neither can yield. Neither can collapse. To understand what this means, you have to accept an unsettling fact about reality. The particles that make up everything you can touch, electrons, quarks, photons, are not solid objects. They are disturbances in an underlying field, ripples on an ocean. And like any ocean, that field exists whether or not anything is moving through it. The vacuum is not the absence of the universe. It is the universe at rest, and even at rest, it has energy. Inside a gravastar, that field was compressed at the moment of collapse to the maximum density that physics allows before the laws themselves break. It cannot be squeezed further without doing what a singularity does, simply erasing the rules. So it does not. It sits at the boundary, permanent, patient, indifferent. An eternal stalemate between two absolutes. If you fell toward one, you would die long before the surface. The tidal forces near an object this massive would pull you apart particle by particle. And if your scattered remnants ever reached the shell, the atoms themselves would cease to exist, dissolved, absorbed, converted into the vacuum energy within. You would not be destroyed. You would become part of the nothing inside. But are they real? A century ago, that question hung over black holes. The equations produced them, but for 50 years almost no one believed they were physical objects that could actually exist. Too extreme, too strange. The universe, most physicists felt, would find a way to avoid them. Then, we saw stars orbiting invisible objects, light bending around empty space. The first approximate image of something that should not exist. The math had been right all along. Gravastars occupy the same position now. The equations permit them. They require no singularity. They destroy no information. They resolve the two deepest contradictions black holes create. And from a distance, they are indistinguishable from black holes, almost. When two black holes collide, they produce gravitational waves, ripples in space-time that travel at the speed of light. We have detected them. The signal arrives as a sharp, brief impact, a resonance that rises and then stops, clean, final. But when two gravastars collide, the shell, a real physical surface, would ring. The gravitational wave signal would carry echoes, not a struck drum, a struck bell. The difference is subtle, but it is there, written into the mathematics of what a surface does that an event horizon cannot. Scientists are listening for exactly that signature right now, but the gravitational fields surrounding these objects are so intense that most of the signal is buried. Our detectors are improving, but they have not yet reached the sensitivity required to hear the echo through the interference. So this is where we stop, not because the story ends here, but because we do not yet have the instruments to write the next chapter. There may be objects out there, colder than anything in existence, wrapped in matter with no name, holding compressed nothingness that outweighs stars, that have waited in silence since before we existed. Or the equations that describe them may be elegant and empty, beautiful mathematics pointing to nothing real. Either answer is unsettling. The universe has never owed us resolution. It has only ever offered us the next question, and the patience to sit with not knowing the answer.